Welcome everybody to the second tutorial of Global Game Jam Prep Week. These tutorials are meant to help you at the Global Game Jam, which is February 3rd to 5th. Today we have Angela Siegel. Angela is one of the mathematical computing faculty at Dal, and she's taught so many courses in first year programming and across, the years. And she's going to look at first year, second year, third year, fourth year. She's going to tell us about how we can design our algorithm and how we can think of gamefully creating from mathematical computing these gaming systems. So a lot of times when we're playing games, we don't always think about the math or the structure behind them. So this is our opportunity to think about that and to plan that. And it's done in pseudocode so that it can apply to any language that you might use at the Jam. For anybody who is hoping to get specifically Unity tutorial, that's on Thursday. And we have a whole list of other tutorials, including cutscenes and VR. So stay tuned and welcome, Angela.
I think it'll follow me straight away. So welcome everybody. Thanks for being here. And I'll just give you a quick background as to where I came from. So I'm here in the Faculty of Computer Science, but my PhD is in combinatorial game theory, which aside from being a long thing to say, means that I spent 4 years doing a game jam, literally. So my PhD is exploring games and mostly strategies for how to solve them. Okay, so today what we're not going to do is we're not going to program. You're welcome to, and as soon as you get inspired and you want to translate that into your language. But mostly I'm going to talk about the thing that I spent 3 of the 4 years of my PhD doing, which is thinking about the play of the game and strategizing and the mathematical foundations of something before you can actually ever touch a keyboard. So I did a lot of programming too, generated a ton of data to get some intuition, but functionally, most of what is really critical is that you understand the games. So how many people have an idea of the kind of game structure they're planning to work on over the weekend? That'd be some hands. It's okay if you don't. Maybe we'll start thinking about some things. So it's okay if you don't have a huge background in this to start really simple. And the examples I'm going to give today are simple games that we can all understand. Probably we've all played and we can explain to each other. Okay, so the first thing you have to do when you're going to play a game is what? Online, I can see what you're writing too, so you can answer as well. In fact, we have a couple of people in the room monitoring that, so they'll just shout out your answers. If you're going to play a game, so let's play a game together. Let's do it. Go. What do you need to know? Sorry, I didn't mean to stump you. So, but like, what would we need to do to actually play a game? I need to set the rules. So there's some key components before you even start. So first you have to picture it. Like, what is this game going to be? I want to create a game and put it out into the world, right? That was part of what I wanted to do with my PhD, but there's a ton of games to draw upon. Okay, so one of the really nice starting points, if this is your first time into this foray into the game world, is think of a game that you really enjoy and just alter it a bit to make it different, change its rule set, make it a bit more fun to play, make it something that nobody else understands. There's a really great example. Okay, I digress because I like to play games. So I'm going to teach you a really simple game, and I'm going to start us off by saying, has anybody heard of anybody that's been in class with me in discrete has heard of this? I'm going to make that smaller. We'll start easy. Okay, Brent, you don't get to answer. Sorry, he's online. He's a dangerous one. So we've got 3 piles of stones. He says fine. It's okay, he knows the answer. We have 3 piles of stones. On your turn, you're going to take as many stones as you want from any one of the 3 piles. Okay, that's the rule. That's the only rule. On my turn, I'm going to take as many stones as I want from any of the 3 piles. Okay, any questions? The rules are clear. We know what we're allowed to do on our turn. I'll tell you that we alternate play.
What is the goal?
What is the goal? Okay, so there's a couple things that you need when you start off. and we've identified the majority of them. We need the rules, and we want to win, don't we? An important point of this, though, when you're creating games for the world, sometimes the goal is the play. There's a whole field of German games, like board games and things, card games especially, that the whole goal of the game is to play. Anybody ever played the game Flux? You either love it and know you love it, or you played it and you hate it. There's no one that feels halfway about this game. It's FLUXX. Give it a try, and you're going to fall into one camp or the other, and every friend you play will be in one of those two. It's a love it, hate it game. The purpose of this game is to play. And so the goal changes frequently throughout the games. It's, to me, as a person who spent 4 years trying to figure out how to win and strategize, it drives me crazy. I hate this game. But when I played with young kids, super fun, because it just keeps them all, they all have a chance. Okay, knowing how to win is important. And knowing if that matters. Like if you're creating a world, you don't necessarily want to lose people, right? You want to have something that keeps them motivated to keep coming back. So this notion of winning is definitely something that we've contrived. But I like to play games where we win. So every game that I play with you, we're going to have a way to win. It's all about this strategy. Okay, so the way that you win is you take the last stone. So we've got 3 piles. We're going to alternate play. And the last person to get a stone wins. Would you like to go first? Oh, okay. I see people shaking their heads. And so I'm curious, maybe we'll leave you out of the game for a second. Would the rest of you like to go first? You wouldn't? And nobody wants to go first? Who would like to go first? What would you like to take?
The 3rd pile.
Did Brent say he didn't want to go first? Is that the problem?
No.
Brent, you'd be good. What's that? This pile? Okay, so we're going to take this away. And I'll say, that's great. I will take this stone. Okay, next to the peanut gallery. Online, you can suggest a pile to play, and we'll call this pile A, B, C.
You can only take from one pile, but we can take as many as we want.
You can take all the stones from any pile. Yeah, up to and including all of the stones. You can take one or more.
So I can take stones from both the piles?
Nope, only one pile at a time. And you're starting to see the problem.
A man wants to do 3rd in C.
Okay, we're going to take just one stone from C. Is that correct?
C. Yes. C.
Okay, and I'm going to play Tweedledee, Tweedledum. I'm just going to do whatever you do. And anybody see these few that didn't want to play first are saying, yeah, I don't want, this is why I said that, right? So why is it that I was pleased when somebody was willing to play first? And now the online gallery can weigh in, of course, again as well.
Mohammed taking B1.
B1, okay. So what happens is no matter what, at this point, in fact, I'm going to go backwards and say, nobody made a bad move. There was no good move. Okay. So as soon as you played anything, I could win, right from the start. So when you play this, I just said, well, I have 2 piles of 2. I'm taking it 2. Yeah, and whatever you do, if you had instead taken 2, I have 2 to take as well. So I was sort of joking that I said I played Tweedledee, Tweedledum. I didn't think. I just copied you, right? So monkey see, monkey do. Tweedledee, Tweedledum, I kid you not, in mathematical, in combinatorial game theory, it is a way to play. So if you end up in a situation where you can replicate the other person's move, going second, you've won. And you don't have to evaluate the game further. So we're going to play more games. Okay, that's what we're here for. But I want you to think about that because this game is called, it's a really important game in math, in life, really, come on. It's called NIM. The game of NIM was introduced in 1903. And it was just a simple game that you could play during war times, like just 3, piles of stones and you take turns, and then it was solved, right? And the solution is mathematically beautiful. And it's computationally, from a computer science realm, beautiful because it's based in binary. Okay, and I'll tell you that even though you might have thought, well, we started, just heads up, this is where you went first. Pick a different location. So go first again. You know, I'm being kind, giving you the first choice. Anytime a combinatorial game theorist says, why don't you go first? It means they know they can win going second. So you should probably just say, oh, no, after you. But because I'm at the front of the room, why don't you go first again and take a different choice? Yeah, see if you can beat me. Great idea. So now those of you that heard that there's a strategy called Tweedledee Tweedledum, I want to put myself in a situation so that I can always copy you. What situation puts me in that place?
Take 2 stones from C.
You betcha. 2 stones from C. Okay, and so now whatever you do, I can copy. And so now I know I've won, but I knew I won from here. And that is because when you think about that Tweedledee Tweedledum scenario, what I wanted was to have a pile that looked like your pile that I could play in.
So if you take the third player?
Okay, yeah, try it. Always good to try it. So that's the number one thing. I said that I spent 3 years thinking about it. Part of what I did when I was thinking about the game was I wrote code and I generated data. Like I would run a game and see who won, who should have won. Okay, and then I tried to figure out, well, why was that the case? Like, what is the strategy there? Okay, and then I proved it inductively. Induction does come into play. Okay, so what do I do if I play in C? Sure, take them all. I totally did. You just didn't notice. So what I see that you've done, all I have to do is get myself to a position where I can copy, and I knew that I could. And I'll show you why. So I called them A, B, and C, but really you could have called this, we had 3 here, 2 here, and 1 here, right? So what you could think of is piles like this. And if you think of it like that, now you're thinking in binary, right? This is 1, 1. If you don't know what this means, don't worry. We'll get you there. Just see that I've got powers of 2 that I'm representing in these circles. Okay, and I know for all of you here, you would have seen it because you would have had me for discrete maybe. Okay, so when you took one of these, if you go like this, now I'm in this weird situation where I look at what I've left over and I've got a singleton. What can I do? I remove it down so I have the same, I have 2 of every binary pair. Okay, so that's actually the strategy of NIM, and it works no matter how many piles you play. So one of the things don't worry, we're not gonna play NIM all day, but this is so you can win in life, or at least in really pubs, bets. You've got matchsticks or something and it's straws. How do you win this? Now it looks a little different, but the concept's still the same. If I break this into binary pairs, what do I have? I've got a 2, a 1, I've got a 4, and a 1. Who wants to go first? Now I actually am being kind. Because I'll give it a shot. Why not give it a shot? I made you suffer through. So what if I did this? What have I just done? One thing, I brought us back to the game we were playing last time. So that's kind of mean, because you knew that in that game, I wanted to play second. So by volunteering to go first just now, I'm kind of being not so kind, because now I made you play first in a game you always lost. Okay, so this notion of understanding the structure is really important. So here's the thing. This game is very well understood. You can't solve it. It's been solved multiple times, but not that long ago, when I was doing my PhD, somebody said, this is a fun, easy to explain game. It actually has an incredible mathematical structure under it. Every single impartial game, meaning games where both players have the same set of rules, is based on this game. That's interesting. And in fact, the value of a game is based on, so if you have a nim, one single nim heap with n stones, it has a game value called star n, okay? And everything about impartial games is based on stars. So it's star 0, star 1, star 2, star 3. Every single game value comes back to the game of nim. I really wish I had created that game in all its simplicity. When I was doing my PhD, somebody said, well, what about misère play? And misère play is just when you flip the winning condition, okay? So what if instead of saying the first person able to take all the stones wins, what if I instead say, I'm going to change that, and the first person who takes that last stone loses? Now, this is a really simple game, isn't it? We understand it. We could probably play it. We could probably generalize it to bigger concepts. Everybody see why this taking the 4 was the easy answer? Before I erase that, I mean, aside from bringing us back to the same game, here's what it comes back to. I broke it down into binary, right? So 4 and 1, 2 and 1, 2. And what I can see is if I look at what's left, if I can remove, this was the one that stood out on its own. Okay, if I can remove this, I get to a place where I can pair them up and I can play Tweedledee, Tweedledum. And that's the goal. Okay, and so, okay, so now I'm going to go back to our same starting game, which is so simple, and we're going to play a new version. Okay, and it's called misère. Now what do? You do not want to take that last stone.
I want to start.
You want to start, okay. And I'm going to let somebody online play the alternate version, okay? So you're going to play each other. You want to not take the last stone this time. Okay, Brent, you're even allowed to play now. Okay. You want to start, and where would you like to go?
Take the top stone from the first pile.
Top stone from this pile?
Yeah.
Okay, I'll label it again. A, B, C. I went the other way just to keep you confused. Oh, I lost them. Oh, they're back. Okay, online team. Anybody want to play in A, B, or C? I better stand over here, otherwise you won't see it. I don't know if they can even see that. I should use the dark. Very, very early. Look, we're gonna get dark. Oh no, that's sad. That is worse. We'll stay blue. This is as good as it gets.
I see that I already lost.
You see that? Oh, see, you guys have hope. Okay, we have a few people for C, and you want to take D2. Oh, I think they're probably going this direction, huh?
Even A2.
Okay, we'll rename them for them. They're just correct. Okay. Okay. Do you want to take online people? Do you want to take that last stone? You do not. Oh, they're changing their answers. They forgot. You could have won there.
Yeah.
Okay, and so, but actually I'm gonna hold you to it, and then we'll let you undo that in a second, okay? So we're gonna let them rewind that in a moment. But what they said they wanted to do, you know, it's that rule. You pick up your hand on the board, it's done, and you just lost your chance. So they're played 2 in C. Okay, we will redeem you in a moment. And they quickly changed their mind. And you all, I hope, were taking a deep sigh of relief because you realize you have an out. Yeah. What's our out, folks? You don't want to take the last stone.
Take B.
Take what?
Take both stones at B.
Take 2 from B. Okay, sorry guys, you get this one. And so when we talk about whether or not a game is won, okay, no offense to you online, but did they play optimally? No. So when we talk about a game and whether or not the computer has won, right? It's based on optimal play because a computer can look through all the possible solutions, or it has an algorithm that it's following to decide what it would do in every scenario. It knows to play Tweedledee, Tweedledum. It knows the binary representation of everything. And so it can figure that out really quickly. Okay, we can't as quickly. Yeah.
The optimal play here always go in second.
So that's an interesting, we can talk about misere play all day, and there's a lot of combinations for that. But what I want to talk about is, do we see that as optimal play? They made a key mistake here, right? So if I were the computer, and you are, or you will be, as you write your games, everything you do when you decide whether or not you've won is based on the assumption of optimal play. But then you respond to what actually happened. But have you ever played a game online where it's like you lose and you're like, but I have like 15 more moves to make. How did I lose already? Right? Or you play, I don't know, I went to a really amazing conference in Banff International Research Station, and there was this man who, has anyone heard of the game of Go? It's like chess on steroids or something, but it's just a bunch of marbles essentially on a board, a 19 by 19 grid. They're black and white stones, and there's rules around play. And this guy was one of the best in the world. Came to this conference with 38 combinatorial game theorists, professors, and PhD students. We're all doing research together. He came one night as like a show for us, and it was so fun. He had 19, it's 19 by 19 grid, and we had 19 Go players that all knew their stuff, all lined up. I wasn't even touching this. I just wanted to video and watch. It was so cool. And so we had these 19 players that were all very good in their own right. He walked around and would move, and then would move, and then would move. And in the meantime, these professors of 20 years that have been studying this for decades are like sweating. And they're like, what do I do to respond to this? And this guy, he's like 20, walks around, just plays as fast as he can walk. And by the time he gets to the next person, like, that was not a good move. And he plays, and he knows what you're going to do, and he knows what you've already done wrong. And he would get halfway through and he's like, you've lost. And then he would carry on, and the person is like racking their brain trying to figure out how they've lost. And he came back to them and he said, we can play some more if you'd like. And he'd let them go until they realized they lost, but he knew. And I mean, that is not to say, so most humans, he played optimally, right? He played as good as he could have, probably in every one of those situations, except one. I remember distinctly, he was playing 19 people. So he had a lot in his brain, and he made one move, and the second he set it down, he was like, you have a chance. He lost. He still won. He won all 19 games. But there was one that he believed he should have lost, because despite being a very clever man, clearly knew his stuff, he knew he'd made a mistake, and he didn't make the move that he ought to have. So, online redemption. What should we have done here? Sorry. If you know me, you know I digress. So what would you like to do to redeem yourselves? I think they already said it before.
Middle in C.
A middle in C. Okay,
Okay.
one of them. All right, folks, do you have a way back?
Wait, did they?
It never, okay, so I'm gonna give you, I'm gonna clarify one thing. You're right. It does kind of depend on their move. And there's some times where you as a human can make a choice that you're like, maybe they won't see it if I do X, Y, Z. But when you're programming and you're making a strategy for how you approach this, it never depends on their move, right? You know, as a computer, whether or not you've won or lost, because your algorithm tells you there's no real comeback unless, and this is the big unless they make a mistake. Okay, and the good news is the computer, they make a mistake. We're human. We make mistakes all the time. It's all good. you might have a chance. But do you have a way you can win?
You can choose both the B.
No. Yes, we.
Okay, let's do it. We can make mistakes too, but because I said that, whenever I let you do something, you know it's a problem. Who's happy on mine?
I'm still with the mean rules.
I know, they did it too, and I made them stick to it, so I have to be cruel. So now, no matter what happens, they take this, you have to take the last one. So redeem yourself. So they redeem themselves. Well, actually, technically they didn't. In fact, they had no way out. Okay, so to be fair, I'm kind of being mean to the online folk, because is there anything, can you see a way from here? If you were playing online, and if you're online, you are you, is there any way out of this mess? Can you force the second player to take that last stone? How?
You can take the 1 stone on A.
Okay.
Wait, am I playing as online or am I playing as?
You're online.
I'm advising on behalf of the online.
Yeah, you're talking, they're not answering, so they're not typing fast enough. I guess you get to advise them. But you're trying to help them win, right? So then, does that guarantee them a win?
Online is suddenly saying, hey, take 2 pieces, middle and C.
Oh, they've got lots of options. Okay, so they want to take middle and C. Okay. Actually, now they're you, ironically. So it's a bad, where I think we've gotten backwards. So from here, the answer is this. Do you want to play first or second? Do you want to go now, or do you want to let the other group go? It doesn't matter which group you are. Do you want to play first or second? And ultimately, to some extent, this is something you can battle out as much to the end of time. This game, and the reason I bring up Misere Nim is this. So I want you to think about it. Think about if you want to play first or second while I digress. The reason I bring up Misere Nim, Nim was around from 1903 until whatever year that was that Misere Nim was introduced. So Misere games, this notion of just flipping the winning strategy, was introduced not that long ago. Like it was in the 2000s at least. And the concept is pretty simple, right? Like, what if we just say, I'm sick of losing to these people, so let's just change the rules of how you win. But it changed the play entirely, where it was really easy to have a Tweedledee, Tweedledum strategy in Nim. Misere play is different, so it looks very different. I could have all sorts of fun on Misere Dim and Misere games in general, and there are strategies that tie back to the original game. But the point is, when you're thinking about a game that you want to approach, you don't have to start from nothing. Sometimes just changing a little detail about the rules of play, about the goal for how to win, changes the game and the feel of the game, the flow of the game entirely. It changes the underlying mathematical structures that determine who wins entirely. Okay, so this is the class, and I'll say it again. These are called impartial. And that just means for both pairs playing, we have the same rule set. Can you think of a game which is not impartial, meaning your rules different from my rules if we're playing each other? Just any game that we've played before. Yeah.
Party 3-on-1s.
That's a fair option. How about some simple games that you, even like basic games you played as kids? Uno? We don't all have the same rules in Uno? Do we? Do you have special wild cards?
Hide and seek.
What's that?
Hide and seek.
Hide and seek? How about things on boards to narrow it down into a focal point?
Snake and ladder?
Snakes and ladders?
Yeah.
Red
Yes.
says red light, green light.
Red light, green light? Oh,
Or you have a bunch of people running, you say red light, green light. It's like whoever's
so
moving on.
that's, I think people are giving me impartial games, right? So that's a perfect Red light, green light is impartial. We all do the same thing, right? Somebody says green light, I run, and your red light will stop until and hope they don't see us. But if we were all playing that game, we all had the same set of rules. How about chess? Okay, now let's just stop for a second. Let's talk about whether or not it is the same. Okay, so there are some things that seem like we have the same rules, but in fact, the rules are different. Okay, go. I'll give you a hint. There's black stones and white stones. Chess, there are white pieces and black pieces. Okay, anytime you see two colored pieces, it's a red flag that it might not be impartial. And that is because you can't move all the pieces, can you? So chess, everybody gets a horse, everybody gets a king, you get two bishops, you know, you have all the same pieces. When you start, it all looks similar. But in fact, your rules are different than my rules. I think you stated, I never remember who goes first. I have to Google it every time. White goes first. That seems just wrong, but anyway, white goes first, and that makes it inherently different because you don't get to decide if you go first. If you feel stronger going first, you want to roll. I don't even know how they make a decision, but you want to be the one that plays white because then you're controlling the game from the moment you start. Okay, so now I want to talk for a second about chess because I love chess. So chess is a fun game, and it's mathematically rigorous, which is another thing I love about it. But my favorite thing about this is that until not that long ago, and I don't remember the year, somebody can Google this for me, but humans could beat every single algorithm that tried to win in chess. That's something, okay? Why would that be the case? Is it that fact that our computers were too slow, our algorithms were just flawed? You know, what is it about that feels like there wasn't enough data? Like, why do you think that was the case? Anyone? Were humans just better than computers? So chess, until recently, maybe Rena can tell us what the year was. It's not that long ago. You were all alive. Humans could beat every computer in chess. In the top, not you. I mean, no offense to you. I couldn't. But the top chess players in the world could beat the computer. 2005. 2005. So it's a while ago now. But 2005, we had fast computers. So we had intelligent brains trying to write software that could emulate the game of chess. So why did it take until 2005 for a computer to beat a human? I mean, not that we couldn't beat some humans, we just couldn't beat the top humans. Yes.
I think there's two reasons. One is because after that point, maybe the dictionary for the chess, the engines got much wider, so they could predict like far into the future.
Yeah.
And, also because the chess, while playing with the masters, could learn over time how they played.
That's right. Yeah, so these are all the right answers, and some of it is about the processing speed of the machines, but a lot of it is about that intuition that humans had. So in case you couldn't hear that online, the suggestion was, well, it was a lot of great things that we're going to cover in part of this. So hopefully you can hear some of it. So the notion is that the greatest minds in chess just had more in their head that they were working from, like a catalog of games they played in positions that they look at. So one of the things that a computer is really good at, and you will be able to emulate very quickly, is the last part of the game. So for instance, if we go back to the easy version of NIM, and I were to have started us off with just this position, A and B, it's probably pretty clear what you want to do. Like if I were playing with little kids, I'd say, all right, which pile do you want to go first or second? And you know, right now, this is our normal, I want to take the last one sort of scenario. You're like, oh, go ahead, Angela, you can do it first. And then I've lost, right? Because you copy me. And if I went a little bigger, but I had two even piles, we'll just stick with two piles. Do you want to go first or do you want to go second? It's up to you. Want me to go? Would you like to go? Anyone want to go? No takers. I tried. You know, we talked about Tweedledee, Tweedledum. So even if I made this like 4 piles, 6 piles, 17 stones in each of the 2 piles, you know, you can copy me if you go second. So you have, like, it's easy to build up an intuition for the strategy when the board is small. So at the end of a chess game, I'm actually pretty halfway decent. When we get down to very few pieces, I'm okay. But the start of a game, there's no way I would want to play the top chess players. I would just be, they'd just laugh and they'd say, okay, you've lost. I'm like, I just moved a pawn. This can happen. So what they're good at and what is harder for us to do, and even hard, and why I said I generated a bunch of data before I got to that end of solving the game, is building that intuition. So what amazing chess players, like the top chess players in the world that do this professionally, are great at, they have crazy recall of previous boards that they've played. So they'll be, you know, playing and they'll be like, oh yeah, I played against Serena Webb in 2017. I won that game. I'll just do the same thing I did there, right? Oh yeah, played Angela Siegel and smoked her in 2019. I'll just do the same thing. And they just move without thinking because they're just following that catalog. Now, they never played us, but you know, they remember those greats. And they don't even just remember games they've played. Part of their learning is looking at histories of boards that have been played in the past and the moves that won. So they are building a total database of past positions and what worked. And so our computer systems that we're modeling that, we're doing the same thing. But you'd say, well, surely there should just be a move simple as NIM. Some of the games, and this is part of what I'm trying to say, is start small with this. Okay, start with something easy that you can easily explain. If you can explain it to your grandma, the rules, and she could play you can talk to a friend, and in less than 10 minutes, like in 8 minutes, explain to them what the rules are. This is a great game to start with, because you first have to be able to understand what you're playing. You can then branch out, make it more complex, add the little details, go from NIM to Misere NIM to, you know, this fancy rule that you can only play primes, and you can take everything, but I actually explored all subtraction sets. So we said you can take anything except this set. And it makes the game incredibly hard. In fact, then the mathematical structure, which I generated data for 3 years, is crazy. And it's really interesting. Okay, so start small. What was I going to do next? Okay, so I'm going to stop for a second and take a sip of water and ask you, what are your thoughts here now that you started to think about games, and then we'll come back to chess. Anybody thinking the game that they had in mind is actually a little bit more complex? This is a really simple game, right? Anybody have a wild idea for a game that maybe they're going to modify and work up to? Yeah, that'd be a better person to play. Mohammed. Well done.
Going to take this moment to correct. I was wrong. There was a Deep Blue computer in 1997 that won some games, but most computers did not beat humans until 2005.
Yeah, and so it was, I think at that point, the top players would still have breakaways, and that was the big thing. It's like they hadn't really flipped the dial. I knew it. I thought it was 2005. That was just my PhD at that point. I was like, I remember the moment it happened, and we were all like, oh. Okay, so the reason I'm talking about different levels of games and the fact that there's different ways that you can layer games is that it's really common that when you first step into this, if you played a lot of complex games, your intuition might be to just jump in the deep end. And I would suggest approaching this from the standpoint of like building a house when you have a tiny budget. Okay. And that is, and you might say, I've never done that. Well, I have. You may have this really big dream of what you want it to become, and you should shoot for that. And you should make plans so that you can get to that. But plan it so that you can build it in phases. In the house model, you know, you got to make sure you have the pieces that matter. Like in our situation, you got to have clean rules, you got to have a way to win. And be consistent with those, but then you can add on the extras, right? Maybe you just have the 1-bedroom house with a washroom and a kitchen and a little studio space, but then you add on the extra bedroom or the extra who knows what dining room. But build what you need first and then start layering on those extra pieces. You don't need to jump into the deep end of the pool. And then what I want you to do before you get further, so build that out so that you have a direction of where to go. Start small and then think about what that's going to look like. Then play a bunch of games. Make sure the rules that you've created make any sense and have any structure that is interesting. Because the reason, like if this game is really simple, and it sounds pretty stupid, to be honest. Like when I first said we're gonna have 3 piles of stones, and our goal is to just take a certain number from the pile, that sounds like a pretty trivial game that I wouldn't enjoy playing. But how many people were like, ooh, should we do that? You know, at least one point in time, everybody's face was a little bit like, I'll take C2. And that's what makes a good game. It's not that it's complex, it's that you leave people wondering. If the second player always wins, nobody's going to play your game, right? Especially if the computer goes second. Mm-hmm. So you have to have a game that has a hook. And sometimes that hook is just knowing that there's a mixed modality of who's going to win, right? And there's a little bit of a question. So it's really nice when the solution is clean, but there's a mixture of plays. So in fact, every time I add a piece to the board, I mean, aside from 2 players, I can always make a 3-pile. I can make an infinite number of 3-pile heaps that you can win going first. And I could do the same, create the same number where you would lose going first. That's a cool game. And that's why this game is mathematically interesting. Anybody wants to play in with me or learn about it, I am game. Pun intended. I'll go with that. Yeah, I'm trying to think. So in terms of chess, coming back to the house, if you were to build chess from the beginning, and that's what a lot of people did. Like a lot of people wanted to get into like creating something that a computer could do against humans. And so they started from games they knew rather than going small. And so the models that started to be really interesting were the games of chess that just had a subset of pieces. And they said, okay, well, you know, all those pieces on the board, that's a lot of pawns and bishops and kings and I can't see to the end. My computer's not fast enough. Like I'm just working off my laptop. Instead, I'm going to take a subset of that game because it's the game I like. And I'm going to start from that. And what happened is those individuals that worked in that space started to build up an intuition of like they would start small, really small, like a 5x5 board. And there were a lot of computer games that were played on a 5x5 board, then an 8x8 board, and just building out until you get to, I don't even know, I always have to think what the full size is. I have to place the pieces of 3. Yeah, it's 3 and then the 2, so 4, 8 pieces, 8x8. And so building out to the 8x8 board, they started first 3x3, 5x5, 8x8. And if you can do that, you've now understood, like, yes, a 3x3 board is in isolation, but if I could understand wholly a 3x3 chessboard with a subset of pieces, what do I know about the 8x8? Anything, or did I just waste my time?
You know what happens if some pieces are in a 3x3 space in the 8x8?
100%. Yeah, because they still follow the same rules, right? So if black pieces are moving in one direction, white pieces are going in another, and they happen to arrive at a situation where everything is in this little 3x3 positioning, I have a strategy for that small domain. Now, obviously the board extends beyond, so if they escape past, but you have some information. So starting small and understanding that is a really helpful piece. And it's not a miss to start small, it's a win, because now you've built up a repository of information that will take you to that next level. So that's kind of the gist of where I'm coming from, and I'm happy to play a lot more games. There's a ton of games that I can choose from, and in fact, I don't know how much time we have, but I have a favorite game that I always play. We only have 10 minutes. Can I play a game? Okay. All right. Here's one of my favorite games, and if you've seen this, I apologize. Brent, you're out. So it's a game that I first brought to this building before I was in the faculty of computer science. I was a program director for Nova Scotia Math Circles. And so as that might imply, we were interested in math. Except I was in a field that was half computer science. All the things I did were half and half. I think I need just one. Okay, so we have one volunteer and they have to bring their chair. How's that? 1, 2, 3. Yeah, one more. Come on. Oh, I volunteered you. Come on up. Dave, I meant you. I will bring a chair for you though, because I like you.
Oh, I already know there's a lot of things.
Oh, yeah, but now you're just a game piece. So the good news is if you're up front, you have no power. You don't have to think. You are just a piece on my board. I will be a game piece too. Have a seat. I need 4 more people. See, don't you want to come here? We don't have to think at all. Okay, the rest of you, including those of you online, are in charge of us. So we're going to give our names as we go down the. In fact, I can take another one. I can stand up if somebody wants to come be a pawn in my games. No? Okay, you're going to come over here. You can swap with me. Okay, they have colored shirts on, you'll notice. We're dressed in black. And so we are the black team here. You all have the colors. Okay, so we are toads, they are frogs. And the rules of this game, oh, I should have asked you, what are the things you need to know to play? You need the rules, and you need to understand the goal to win. Okay, our rules are as follows. Toads, we have 2 things we can do. We can move over 1, or could you slide over for a second? If we happen to see a frog next to us, we can hop over them. The one thing we cannot do, slide over please. Oh, both of you, 2 of you, any of you, is we can't land on another frog. And I can't jump any further than this. I'm limited. I'm a toad. Okay, so I have no move right there. Okay, so toads, you can do the same thing except in reverse. You can come this direction. 1, and slide back. Sorry, you're gonna get a lot of, it's like a squat. It's a free exercise class with me. You can also hop over me. Toads go this way, or sorry, frogs go this way. Us toads go the other way. That's it. It's as simple as that. Again, this is one of my favorite games for mathematical structure. We could have talked about this the whole hour. The underlying structure for this is brilliant. So your job is to get us from side to side. We want to swap positions. Toads are moving over there. Move us.
So who's?
These are your beautiful frogs. They're very colorful as frogs can be. Toads a little bit more muted. Crusty. We're wearing all black over here. Sorry. I'm sorry. I think you can take it. I kind of forgot. I also have to do this. Okay. So can we introduce ourselves? So we got Dave. You want to shout out your name? What is it?
Camilo.
Camilo? Rachel? Rachel? Angela? Rena? Hassab. Okay. So, oh, so I knew that too. Sorry. So those of you online or in the audience, I think you can see the online, right? Yeah. Please, if you could, move us. You can pick the toads or the frogs. And first, does it matter? Let me just. Oh.
We can see
Oh, yeah.
all of the
Well, I
play.
kind of have to be in the middle, so cheapers here.
Are we against each other?
You are all on the same team. Your goal is to get to the end. So technically, we could alternate play, but because of time, we're trying to get it done. And what I want you to think about is so mathematically, when you think about the structure of a game, the first thing that you think about, so remember I said impartial or partisan. We are different pieces. That means even though we have a mirrored set of moves, we don't actually have the same moves. And so that's a really different thing. And I should have been more clear about that with chess. in chess, there are white pieces and black pieces, and the difference isn't just that white goes first, but if you look at any place spot in the board, like we played a little bit and our pieces are all moved around. If I'm playing white pieces, I can't move the black pieces. I don't have your moves available. Like if you can put me in check, I can't necessarily put you in check. I have a different set of moves. So when that's the case, it's called something different. It's called a partisan game. Just for fun, it's good to know what you're playing. Okay, so if there's two sets of pieces, it's probably partisan. All right, so go. The next thing to notice, the board is symmetric. When there's symmetry, there's sometimes a really clean symmetric algorithm to the movement. So despite the fact that we are going in different directions, we don't actually have the same pieces, same set of move sets, and there's a symmetry to what we're doing. The structure on this is beautifully symmetric.
So the dots have to go this way and the frogs have to go.
Yep, toads go this way, frogs go that way.
But like, is there any like winner? I think.
I mean, we all win if we all get to the other side. We'll go with that for this one. So sometimes it's just about solving a puzzle, and you can think about that. There are games where the win is solving it. And that's why I like this game. That's like a game. Has anybody played Rush Hour? You're not playing anyone else. You're just playing, or solitaire, those types of games. You're just playing to have fun and solve it. And I love those games because then everybody's a winner. So we're going to win together. We can do it. Okay, it's symmetric. What does that mean? Does it matter if she goes or I go? No, they can't jump over me. I can only jump over one frog. She can only jump over one toad. So you can go first if you'd like. Okay, Rachel moved. So who should go? And how many moves are there?
One move per.
Now, how many of us have an option to move? Let's raise our hand up here if you can move. Oh, I can move too. Okay. Who thinks I should move? The only person that can move, there's only two of us that can move. I can move, we can only go this way. So this is the crux of this one. I can go this way. So I should go?
Yeah.
Is that the thinking? Okay. All right, raise your hand if you can move. Who should move? Rachel. Who can move? Toads can move and the frog can move, yeah. Who should move? Toads? Toads, they said toads first. I'm gonna hold them to it. Sorry. Okay, who can move? Oh, who should move? Frog should move. But they said frog first. Yeah, it's you, Rachel, sorry. Okay, and who can move? That's a bad sign. So we're not at the end and only one of us can, but come ahead and move. Yeah, and who can move? Oh, just Rachel, go, frog, go. Oh, no. Who could move? No one. So this is a pretty simple game. The goal is to win. We have to reset because we did not win. We can do this quick. We have 5 minutes left. 3 minutes left? 3 minutes. Good, we can do it in 3. Okay, so the problem was what? Actually, I should have stayed put. The moment Rena sat next to me, what happened? Some people went, generally when you have the feeling after you made the move, it means that you made the wrong move. That's another good game tip for you from combinatorial game theory. As soon as she sat next to me, what happened? Everyone to my left, they can't move, okay? It's a symmetric game. What happens if you put 2 frogs next to each other?
The dots can.
100%. Everyone to the right of them is now stuck. We can't hop over 2 frogs. They can't hop over 2 toads. Put it together. The problem. Okay. Symmetry. Who started? You go. Yeah. Okay. We'll start you off. Okay. Raise your hand if you can move. Yeah. Okay. Who do you want to move? Now. And you can't move. Rachel or Rena. And now always keep in mind what gets you stuck. Putting a frog and a frog together, toad and a toad together, we get along, but we don't let the others past us. But they want you to move, Rena.
Online says Rachel.
Uh-oh. Uh-oh. Okay, now we're stuck doing this, so it's okay. So as long as we don't get ourselves stuck further, so now raise your hand if you can move. Now I want you to think, the thing that gets us stuck is what? 2 toads together. or two frogs together? Which one puts us in a bad situation? Yeah, he's a problem. I'm sorry. I know, it's your fault. So Rachel's gonna have to take us, okay, so raise your hand if you can move. Okay, who gets us stuck? Oh, it's a toad's causing trouble. Yeah, Rena, it's your fault. Don't get us stuck. So there's only one choice. We only, at most, we have two players that we're choosing from. But one of them is a problem. It's always one of us. So you move. Okay, now raise your hand if you can move. Which one gets us stuck? Oh, this is confusing, isn't it? Now we have to think. And now it would benefit to being world-class toads and frog players because they would see beyond this move. They would say, oh, I've been in this situation before. If I move Dave, then Angela, or if I move Angela, then Dave has to move and he's next to someone and then Rena's stuck. Okay, so sometimes it's one move ahead and I'll just play that out. If I move Angela, then Dave has to move. And then I've just put two frogs. Now you got to do it. You haven't had to move all day. Look at all the exercise you're getting. You've just put two frogs together. Okay, back. Now you get to move again. So it's just beginning for you. So when I moved, one move later, we got stuck. Okay, so sometimes it's also about forecasting. So unfortunately, Dave, you're gonna have to move again and again and again. Okay, and now who can move? Just me. I'll do it. Okay. So who can move? Just Rena. Either of you can. Raise your hand. Yeah, you can move, but he's a troublemaker. So don't move him because he goes next to another frog. So Rena's got to go. Awesome. Who can move? Yep. Absolutely, because if we move the frog, we get two frogs together. We need our toads. Now we're getting you moving. You've been stuck for a long time. Okay, who can move? Yeah, I guess so. I'm sorry, I should have put you in the middle. Off you go. You're the only choice. Who can move? Only one. Well, that's an easy choice. I'll make that one. Off you go. Who can move? Only one. Oh, wait, no. I was wrong. I would have made us really troublemakers. You'd be stuck with us forever. Dave can also move. So now take a look at that. Who should move? Dave. Otherwise, we put two toads together and we cause trouble. Who can move? Just Rena. Come on. I want you. All right. Who is next? Only you. And yeah, the toads were anyway. And the frogs got together. So in the last few minutes, you solved the game, you walk away having problem solved, and that little silly feeling of solving something is why we make games. It's so fun when you get it right. It's so frustrating when you get it wrong, but part of that frustration and having a hook in there that you can make a mistake is part of what makes it a challenge and kind of fun, right? So this is simple, NIM is simple, chess is not. Start with something simple. That's the takeaway. That's a big takeaway. All right. Thank you all for coming and good luck this weekend. Super fun.
Thank you.
So thank you, everyone. There are more tutorials. Please come out to them and please follow on shiftkey.labs.ca/GGJ to find the full schedule.
GGJ.
GGG.
Oh, Global Game Jam. I got it.
Yeah.
I never added the G before.